Hey APES crew, it's Miss Lenorovitz, and this video is just going to give you an introduction to two different styles of problems that you're going to be working on in this problem set. So the big theme is energetic math, but each of the problems that you're working with is going to focus on using metric conversions and using dimensional analysis. So you're probably familiar with a lot of the prefixes that you're going to see on this chart here. These are ones from the scientific notation that you need to know as part of APES, so feel free to refer back to these. I anticipate that you've probably used quite a bit, and we've used a bit in the class from the area around milli and centi, and you're probably familiar with kilo and mega, but you're going to be using both the upper and the lower extremities of this chart as you're working through these problems today. So I'm going to take you through an example of how to set up a problem like problem number 1, and then also how to set up a problem like problem number 4. So we'll do that one at a time, starting with problem 1. All right, so problem number 1 asks you to go from the current concentration of carbon dioxide in ppm to express it in percent, to express it in parts per billion, and to find the concentrations of at least 2 other greenhouse gases of concern. I'm going to be using the data from an older problem set, so this one is actually from February 2019, so you can mentally check and see what has happened to the concentration of carbon dioxide over the last 3 years. I wish I could say the trend was different, but it is definitely increasing. So let's start with that first question there. You have a concentration in ppm, or parts per million, and the question asks you to express it in percent. Remember that in this whole problem set and in any math that we do in this class, you want to make sure you're showing your work, showing your units, and showing your final answer very clearly. So we have 411.8 ppm back in February of 2019. So another way of representing that is 411.8 parts out of 1 million, or over 1 times 10 to the 6th. And we want to express that in parts per 100. So parts per 100 is 10 to the 2nd. In order to get from parts per million to parts per 100, we're going to have to divide by 10,000 by 10 to the 4th power. So you can actually do this without even using a calculator if you're using scientific notation. So if I am dividing this by 10 to the 4th, I am subtracting that exponent, 6 minus 4, to get to 0.4118 over 10 to the 2nd. So our percentage then is 0.4118%. If I am expressing 411.8 ppm, and in question part B, it asks for that concentration in parts per billion, I can do that same job here. So again, we're starting off with 411.8 parts per million. So that's why it's over 1 times 10 to the 6th, or 1 million. If I express that in parts per billion, it's going to be a greater concentration. So I'm going to multiply this by 10 to the 3rd. When I do that, the numerator is going to be 411.8 times 10 to the 3rd. The denominator is also going to get multiplied by that, which will be 1 over 1 times 10 to the 9th, excuse me. That gets us, when we simplify that, to then 411.8 times 10 to the 3rd ppb. So if we were expressing carbon dioxide concentration in ppb, that value would be larger. The last part of this question is something that you can look up on your own. The values that I've represented here represent values from 2019, so you're going to want to update those for the current concentrations in the atmosphere. All right, the second part of this video is going to focus on question number 4 to walk you through an example of how to deal with energy problems. In reality, they're not much different than the problem that we were just looking at. They're going to use scientific notation, you're going to use those prefixes, and you're going to need to use dimensional analysis to show your work. This question asks, according to the U.S. Department of Energy, a typical U.S. household uses approximately 900 kilowatt hours of electricity a month. A typical power plant uses 324,000 megawatts per month. So we're trying to figure out what is the power plant's generation in kilowatt hours per month, and then how many U.S. households could the power plant supply with electricity. Well, one thing that will make that a little bit easier is if we know a little bit more about the terminology. So one of the things I encourage you to reference as you're working on this problem set is the energy terms handout that is linked for you in Google Classroom. Here, you're going to see an introduction to units of energy, many of which you're going to have heard of before. Kilowatt hour is one of those. And you're also going to see units of power. This is the rate at which energy is used. So you'll see that watt and kilowatt themselves are actually units of power. I encourage you to read through this handout before you delve into this problem set, just to familiarize yourself with those terms and then to use it as a reference as you continue to work. All right, so let's take this question one part of it at a time. Part A asks us, what is the power plant's electricity generation in kilowatt hours per month? So really, this is just asking us to convert from megawatt hours to kilowatt hours. So it's really just a problem of dimensional analysis. Again, you're setting it up using dimensional analysis, and if you're setting it up using scientific notation, you really aren't going to need a calculator. So how do we start this off? We start off with the value that we know already. So we're told that it produces 324,000 megawatts per month. So that's 3.24 times 10 to the fifth megawatt hours. So the capital M stands for mega there, per month. We want to convert that into kilowatt hours per month. So one of the next thing that's going to be helpful for us is to convert from megawatt hours into watt hours. A megawatt hour is equal to 1 million watt hours. So I've set up my conversion factor so that the megawatt hours are on the bottom of the fraction. I'm not quite done with the problem yet, so now my answer is going to be expressed in watt hours. I really want to express it in kilowatt hours. So the next conversion factor that I'm going to use is that 1 kilowatt hour is equal to 1 times 10 to the third, or 1,000 watt hours. Now I can go back through and I can cancel out any units that are in both the numerator and the denominator. So megawatt hours cancel out, watt hours cancel out, and what I'm left with is kilowatt hours, which is great. This is a good way to check and make sure that your problem is set up correctly so that when you go ahead and do the next step of calculating the value, you know that you've got the chance of getting the answer correct. So now I'm going to multiply across the top. So I've got 3.24 times 10 to the fifth times 1 times 10 to the sixth times 1, which is 3.24 times 10 to the 11th. The units I have left on the top are kilowatt hours. On the bottom, I have left months times 1 times 1 times 10 to the third. From there, I can go ahead and further simplify. 3.24 times 10 to the 11th over 1 times 10 to the third simplifies to 3.24 times 10 to the 8th. But my units of kilowatt hours on the top and months on the bottom stay. So it's my final answer there. For part B, this is asking us how many U.S. households could that power plant supply with electricity? Well, we know that the power plant supplies 3.24 times 10 to the 8th kilowatt hours per month. And we know that a household uses 9 times 10 to the second, or 900 kilowatt hours per month. So I can multiply by that fraction, and we find out that I get 3.24 times 10 to the 6th households divided by 9. Here, again, you can simplify, you can do the math on your own, but that gets us to 0.36 times 10 to the 6th households, or we can further simplify that to 360,000 households. So hopefully that was helpful in terms of a way of looking through two different styles of problems in this problem set. See what you can do.